So, hello.
Hi, Rainer.
Hi, Giuseppe. Can you hear me?
Yes, yes, just a moment. Okay, I allow you to present. Okay. Okay.
Okay, I will try and share my screen, right?
Yes.
Let's see. Um, so, can you see the slides?
Yes, perfect.
Okay, I would actually like to leave it in that format, if that is okay.
Yes, I think it's okay. No problem.
Okay,
Okay.
should the screen freeze, please let me know if you have that impression. Then
Yes.
I can try and do something about it. Okay. Let me know when I shall start.
Just now I will present you. Okay, the next speaker is Rainer Verch, and he will talk about the temperature and the entropy area relation of quantum fields near outer trapping horizon.
Okay. Thank you to the organizers for having me and presenting this talk here. The title has already been announced, so I would like to comment that this is a joint work with Fiona Kopitz, who is a student at the Institute of Theoretical Physics in Leipzig, together also with Nicola Pinamonti from Genoa, and I think you all know him. So if you would like to look at further details, you can do that in our preprint, which is on the archive. Right, so let's start. So this talk has to do something to do with black holes and black hole thermodynamics. And I remind you of the laws of black hole thermodynamics as has been formulated by Bardeen, Carter, and Hawking in 1973 for actually stationary black hole spacetimes. And there is a zeroth law, which says the surface gravity kappa is constant on the horizon. There is a first law, which says that the mass energy variation of a black hole, this is that dm, is equal to kappa divided by some constant times the variation of the horizon area plus some work term, which in the following I will not consider. And there's a second law which says that the area of the black hole, A, can only change in time by increasing. These considerations have been done entirely within classical space-time geometry, and I'm using here geometrized units. Right, and these laws of black hole dynamics or black hole thermodynamics are very reminiscent of the laws of thermodynamics in equilibrium. So you can identify some quantities of a black hole with the quantities of a system in thermal equilibrium, and then you see there are corresponding laws. And so you would, for instance, identify the mass energy of the black hole with the internal energy of a system in equilibrium. Then the surface gravity would correspond to 1 over the temperature, the inverse temperature. The surface area would correspond to the entropy. And there are also some identifications for the work term. Now, the question came up if there is something more to this black hole temperature beyond a formal analogy. And actually, the origin of black hole temperature can be explained within quantum field theory in curved spacetime, as was done in Hawking's iconic paper in 1975 on the Hawking effect, where Hawking considered the scattering of a quantum field theory, a free scalar field, on a spacetime with a classical matter background collapsing to a Schwarzschild black hole. So initially, at very early time, the idea is that the matter, classical matter, that induces the classical gravity is very thinly spread and the metric is approximately flat. And the quantum field state is approximately a vacuum state. And then at very late time, finally, the matter is collapsed to a Schwarzschild black hole. And the quantum field state settles down to a KMS state, an equilibrium state, with respect to Schwarzschild time outside of the event horizon at an inverse temperature, beta, which is given by 2 pi divided by the surface gravity of the black hole. And the surface gravity is a geometric quantity, and for Schwarzschild black holes, it is proportional to 1 over the Schwarzschild radius, R of S. Well, Hawking's original derivation has undergone several improvements. There are probably hundreds of papers on that, and I have listed here some of the more influential ones by Wald, by Dimmock and Kay, by Friedenhagen and Haag. But just to say, there is a very large number of other papers devoted to this Hawking effect. It had also been noted a bit later by Sewell that a kind of Hawking effect also arises for static black holes by an analog to the Bisonyanovichmann result on Minkowski spacetime. So in Minkowski spacetime, this Bisonyanovichmann theorem tells you that the Minkowski vacuum state is a KMS state for Lorentz boosts in a fixed space direction, and the inverse temperature is proportional to the proper acceleration of a Lorentz boost. And also, this observation was considerably improved and generalized by a large number of papers. Particularly influential has been a physics reports paper by Kay and Wald. And again, there have been really numerous papers exploiting this analogy. I should point out that all these considerations use the global space-time structure and also the global space-time structure for a black hole. Now, actually, a local concept of Hawking temperature is very desirable. Actually, when one attempts to describe something like black hole evaporation in semi-classical gravity, for instance, one would think that the temperature changes because the black hole changes, loses mass or so. And so one would like to come up with local temperature concepts for Hawking radiation, or at least for some quantum matter in the background of a space-time where the where one has a structure which is similar to a black hole with a changing mass. And some first ideas came up in a paper by Parikh and Wilczek in 2000 with a proposal for a tunneling interpretation of Hawking radiation. And that was formulated in the context of quantum mechanics. And there have actually been very many follow-up papers, again, to this paper. But it is in the setting of quantum mechanics, and that is to some degree a limitation. And one paper that has removed that limitation was a paper by Walter Moretti and Nicola Pinamonti in 2012, where they have given a reformulation of the Parikh-Wilczek idea for quantum field theory in curved spacetime, using a scaling limit of the quantum field theory towards the horizon of a stationary black hole. And our work here is really a generalization of this work by Walter Moretti and Nicola Pinamonti for the case that we don't have a stationary black hole horizon, but potentially we have a black hole which changes over time, where in particular the mass can change with time. There is something to be said about the interpretation of black hole entropy and the black hole area, the entropy-area relation, which has been suggested in these laws of black hole dynamics. And a first attempt had been made by a very famous paper of Bekenstein in 1973, where essentially he said the black hole entropy should be identified with the information lost about states that are falling into the black hole. And he has given some nice interpretation of that in terms of light beams, which traverse the event horizon of a black hole. Bob Wald has given a more geometrical interpretation where he showed that black hole entropy can be understood as Noether charge. In loop quantum gravity, which is an attempt to quantize gravity, the idea was that there is a natural concept of quantization of area, and a quantized unit of area should carry a minimal unit, let's say a bit of information, and that leads also to a proportionality between a black hole area and entropy, at least to first order approximation. In string theory, I would say, not being a string theorist, there's a similar concept saying there are natural minimal geometric units in this approach, which then one thinks carry minimal units of information, and also there with such a concept, however, starting from a different viewpoint, some relations between the black hole entropy and the area have been proposed and shown in certain contexts. There is black hole entropy related to holography, which is a big topic, and to entanglement entropy, but I will not say anything about that. Just mention that both areas are major lines of research. Actually, there is not very much in quantum field theory in curved spacetime. about black hole entropy, and in particular, a relation between the black hole area and entropy, at least to my knowledge. And saying that, I have to point out there are some recent exceptions. There's a very nice paper by Hollands and Ishibashi, which is based on the relative entropy of states. It is a global concept, but it is also in some sense dynamical because it refers to some kind of back reaction. That is Hollands and Ishibashi's consideration, where for stationary black holes, there is a very recent paper by Edoardo D'Angelo, who is, I understand, a student of Nicola Pinamonti, who has made a generalization of these findings of Hollands and Ishibashi in the context of dynamical spherically symmetric black holes, which I will now consider in this talk. I should say that as I see it, some conceptual ideas go back on one hand to a paper by Roberto Longo, where he suggested, at least by means of an analogy in Minkowski spacetime quantum field theory, to consider relative entropy of states in the context of black hole entropy. And Bert Schroer has pointed out in some papers around 2005 that one can obtain, again, for Minkowski spacetime, an entropy-area relation for quantum fields restricted to light-like hyperplanes, because typically these restrictions don't show any correlations in the transversal coordinates, transversal to the light-like direction of a light-like hyperplane. And we will actually come back to this in this talk. Right, so with that, I come to presenting the geometrical setup that we want to consider. There are actually very many local generalizations of black hole horizons that one could consider, all types of trapped surfaces and so on. So the concept that we are relying on or following goes, I think, back to Hayward. And it is here even in a more special situation, because we will consider spherically symmetric spacetimes. So our spacetimes, they can vary in time. You can think of a black hole with a varying mass, but it is not rotating. So the manifold is therefore a product of L, which is a piece of R2, a suitable piece of R2, times the two-dimensional sphere. And the metric takes this form in a particular choice of coordinates, which are the Eddington-Finkelstein coordinates. So we have two coordinates, V and R, for our L part of the spacetime. The R coordinate plays the role of a radial coordinate, but it is actually taken in a light-like direction. So this is a light-like coordinate, but increasing R goes radially outward, if you like, from a center, which you can think of as the center of the black hole. There's another coordinate V, which, depending on this coefficient function capital C here can take any signature, any sign. And we have on S2, the S2 part, the standard Riemannian metric on the two-sphere. So obviously this is a metric, spacetime metric, which is spherically symmetric. And as I said, this is a generalization of a the metric generated by a spherically symmetric central mass distribution, which may vary in time, but it doesn't rotate. And here the central mass or Hawking mass could be expressed in terms of this function C and the radial coordinate in that way. In a more special case, where actually psi, this function psi appearing in the form of the metric, is equal to 0, then one obtains the Verch metric class, which really is a generalization of the Schwarzschild metric with a time-dependent central mass. Now, in this context, one can very easily define the outer trapping horizon, which is the submanifold of points in the spacetime where this function C is equal to 0. Well, you need some extra regularity conditions here. For simplicity, let me assume in this talk that this set has only one connected component and is a proper submanifold. One could otherwise take the outermost connected component in terms of the largest radial function in some sense, which I will not specify here. Anyway, what is important to observe is that in the case that the mass is decreasing in time, that would correspond to the picture of black hole evaporation, this submanifold, this outer trapping horizon, is actually timelike, a timelike manifold. So you have timelike tangents to the manifold. It is if the mass is increasing in time, which corresponds to, let's say, a black hole, which is still accreting mass, then the outer trapping horizon is a spacelike submanifold. And if m, the mass, is constant in time, then the outer trapping horizon is lightlike, and in fact coincides with the event horizon in case you have a Schwarzschild black hole. Yeah, what is the meaning of this outer trapping horizon? So basically, in the most simple terms, this manifold separates the part of space-time where radially outward directed light-like geodesics have positive expansion, that would be the outside, from the part where radially outward directed light-like geodesics have negative expansion. So when you are outside, then outward directed light cones can still geometrically expand, whereas when you are inside, they necessarily have to contract. Here is some sketch taken here from a textbook of Griffiths and Podolsky. This is a sketch of, let's say, a black hole which forms by a radial infall of radiation. So the infall is along light rays. That is certainly very idealized, but it has the advantage that these things can really be calculated. So in this picture, we are essentially using these coordinates, which I have indicated, and the radial coordinate r is along such light rays, actually such path-directed light rays from the center. And here this suggests that in this area we have an infall of matter along light rays, and here from this point onwards this infall has ceased, and the if you like black hole settles down to the Schwarzschild situation. So it is often better to look at such a situation in terms of conformal coordinates, where the light rays are represented by 45-degree lines, like here. And let's just look at this here, which is the event horizon. And this curve here is called here an apparent horizon. And in this situation, it would coincide with the outer trapping horizon. And you see here, since the tangents are always below 45 degrees, this is a spacelike submanifold, and it goes over to the lightlike submanifold once the matter infall has ceased and the central mass is remaining constant. Okay, so this is just one indication. What you also observe now, of course, in contrast to what you may be used to from a Schwarzschild black hole, there is in general no timelike killing vector field, but there is a generalization, and this generalization is particularly connected to the spherical symmetry. So in the coordinates we have used, there is the so-called Kodama vector field, defined like that. And it has properties which generalize the properties of a timelike killing vector field. For instance, it is conserved and also contracting with symmetric and rotation invariant tenses leads again to conserved quantities. So in a sense, this is as good a replacement as you can have. And you can use it also to define the surface gravity on the outer trapping horizon H. It is defined in this way, actually for coordinates such that for points on the outer trapping horizon. And you find that in terms of the Kodama vector field, you have such an algebraic characterization of the surface gravity on the outer trapping horizon, which is analogous to what you have for, let's say, a Schwarzschild black hole, where K would really be the timelike killing vector field, the Schwarzschild time from the generator of the Schwarzschild time coordinate. Right, so now we would like to consider such spacetimes with outer trapping horizons, and what we would like to do is to study scaling limits of quantum fields near an outer trapping horizon. And we do that by choosing particular adapted coordinates near the outer trapping horizon. And actually, given a point on the outer trapping horizon, we can consider its rotation orbit, so its cross-section, its spherical cross-section. And the point is now that we define adapted coordinates relative an arbitrary chosen such spherical cross-section. And here, V is an affine parameter for lightlike for the outgoing lightlike null congruence called script C, and U is an affine parameter for the lightlike ingoing congruence called T star. So the star always refers to the particular choice we have made here, let's say for the cross-section. And yes, always emanating from the cross-section. I will show you a picture on the next slide. Just to say, these adapted coordinates, as said, are affine parameters for like geodesics, starting from the cross-section. And yeah, they are chosen in a particular way, such that if both are 0, then you are exactly on the cross-section. There's also the point that the metric now takes a very simple form with respect to these adapted coordinates. In particular, this coefficient factor here, which is non-constant in general in a neighborhood of the cross-section or of these null congruences, becomes constant on the union of these null congruences. And you can also say something about the projected action of the Kodama vector field in these adapted coordinates. So the projection of the Kodama vector field on this T congruence near the cross-section takes this form. And if you look at that, you would say, well, that looks very much like the action of the killing flow or killing vector field of a Schwarzschild black hole on the event horizon. And notice here the kappa star is actually the value of the surface gravity on this particular chosen horizon cross-section. So here's some here's an illustration. So here on the left half of the page, I've chosen an outer trapping horizon H, which is spacelike. Here, the point represents actually a spherical cross-section of the horizon. Now there are these adapted coordinates, V, which is future outgoing, and U, which is future ingoing, and the corresponding congruences, lightlike congruences, which you get when you take all of them over S star. Now in these conformal coordinates, it looks like this is properly outgoing, but actually the expansion of these geodesics here starting at a point from the horizon is 0. So they don't get away from each other. Neighboring such geodesics in this direction, they don't get away from each other. Here is a similar picture. Now the horizon is timelike. And here the green arrows, they symbolize the Kodama vector field. Yeah, looks a little bit like that. Notice that this point here on the horizon has no components in the u direction. So no components along the T congruence. Right, so now we want to quantize scalar fields on this manifold, and I'm just flashing this slide because I assume you all know how this is done. You can assume that the space-time with the outer trapping horizon is globally hyperbolic, but you actually don't need to. So for our purposes, it is enough to consider quantum field theory in a neighborhood of this particular cross-section, which we have chosen. We take a scalar field, we quantize it in the usual way. So the commutator of abstract field operators is given by I times the advanced minus retarded green distributions. And that is what we need the global hyperbolicity for. So other than that, so I hope you can still see the slides okay. And there's no problem. So quantized scalar field, now states, well, you know what states are. You form the algebra of these abstract field operators, and you have endpoint distributions. And quasi-free states are entirely determined by their two-point distribution. And it is of Hadamard form if we have this particular form of the two-point function, where the most singular part is given roughly by 1 over the squared of the geodesic distance. There is some epsilon regulator, and then there is a subleading singular term, which is determined by the logarithm of the squared geodesic distance and some other geometrically determined parts, and there is a smooth part, which basically comes from the state dependence. Okay, so the Hadamard form, I think this has already been mentioned yesterday in Chris Fuster's talk, is related to a microlocal spectrum condition, actually equivalent to it, which goes back to results of Verch. That has stimulated a very large direction of research in quantum field theory and curved spacetime, and it implies also quantum energy inequalities. That is what Chris has been talking about yesterday. Quasi-free states are building blocks of physical state spaces for quantized linear fields on curved spacetimes. That has been the content of really a lot of research in quantum field theory in curved spacetime over the past decades. In particular, they are, the microlocal spectrum condition has been shown to be instrumental and sufficient to construct generally covariant Wick products, renormalized quantities of, let's say, free fields relevant for the perturbative construction of interacting quantum field theories in curved spacetime in a covariant way. The interesting thing is that the Hadamard condition is not only sufficient, but it is also necessary, as has been pointed out in some previous papers. Okay. Now, the scaling limit at a chosen cross-section. So we define some scaling transformations, and we do it like that. So we choose a cross-section of the outer trapping horizon as indicated. We set up adapted coordinates with respect to that cross-section, we define transformations on test functions. And here we have two scaling parameters, mu and lambda. Lambda will act on test function by scaling the u coordinate towards u equals 0. So this here looks like you take delta sequence with respect to u, and then you actually take you multiply with a delta sequence with respect to v. Okay, so scaling limit now proceeds as follows. You take a Hadamard two-point function, and our result is there is then an open neighborhood of the chosen horizon cross-section, so that a certain scaling limit of this two-point function exists in a neighborhood. So for test functions supported on a neighborhood of the cross-section, so you scale with respect to the u coordinate, and then you localize in the v coordinate, and then you get a two-point function, capital lambda, which looks very familiar in some sense. So notice through this mu equals 0 limit, the v dependence has actually disappeared. But before you take the limit, the scaling limit towards u equals 0, and that gives you something which looks like the two-point function of a free chiral conformal quantum field on the line. So like that. And then you still have an angular dependence, which is expressed here by this integral with respect to the coordinates on the sphere. Okay, one part of this result also then tells you what the killing flow does in this, not the killing flow, the Kodama flow, the flow of the Kodama vector field does in this scaling limit. And it, with respect to the flow parameter of the Kodama vector field, it acts like this dilation with this characteristic surface gravity factor coming in here. So if you consider this on, let's say, Schwarzschild space-time with the event horizon, then you have that the Kodama field is actually the killing vector field with respect to Schwarzschild time t, and then you get this expression, and that I think also looks familiar to you with the surface gravity of the black hole horizon in this case. Okay, now through the scaling limit and restriction, you find a universal two-point function, which can be interpreted as a two-point function of a quantum field, a chiral conformal quantum field with an additional angular dependence. And you can interpret this as a conformal quantum field theory on this lightlike hypersurface of the ingoing lightlike congruence starting from the cross-section. So in particular, if you make this identification of test functions, then, well, you take in the canonical way the symplectic form from the two-point function. You form a Weil algebra in the familiar way. You can take local algebras on this particular T congruence. The 2-point function scaling limit 2-point function supplies you with a quasi-free state, which in a way plays the role of a vacuum state. Then in the GNS representation, you can form local von Neumann algebras, and you have a unitary action of the group of dilations, translations, and rotations, which act geometrically, well, as they should, on the test functions. Right, and as you would suspect from having such a nice vacuum 2-point function for a chiral conformal quantum field theory, you get analogues of the right and left wedge algebras, and you are in a Bisonyanovichmann geometric modular action situation. So the GNS vector is a cyclic and separating vector for both of these right and left von Neumann algebras. The translation group acts and has a positive generator and fulfills this half-sided inclusion relation. But most importantly, the dilation group, which takes the Kodama flow parameter here as its group parameter, that is given by the Tomita-Takesaki modular group, delta IT, of the right algebra and our GNS vacuum vector, apart from a scaling by an inverse temperature, which relates to the surface gravity at our chosen cross-section, kappa k. So, in this way, and that is, of course, equivalent to saying that this scaling limit 2-point function is a KMS state at inverse temperature beta equal to pi divided by the surface gravity with respect to the Kodama flow parameter in the scaling limit. And this is actually a local analog of the Hawking effect in the scaling limit. So I'm not sure how much time I still have. Maybe you can say something.
You have 2 minutes more.
2 minutes more.
Is enough.
Okay, this is not very much. I will just point out there is an interpretation of these KMS states in terms of a tunneling or transition probability, which is very similar to what has appeared in the previous paper by Moretti and Pinamonti. I will skip this and go a little bit further. For the scaling limit theory, with respect to the scaling limit state, you can consider coherent states, and they have a relative entropy to this scaling limit state, which we would call the vacuum. And actually, Daniela has explained everything about that, and in particular, the formula you get for coherent states for the expression of the Araki-style relative entropy. Actually, this has been calculated in 2 independent papers by Stefan Hollands and by Roberto Longo in 2019. What you get is such a formula here. And the interesting thing is that this relative entropy indeed scales with the geometrical area of the horizon cross-section that we have used to construct the scaling limit. So the relative entropy of coherent states scales indeed like the geometric area 4 pi r star squared of our horizon cross-section. Some comment is that this is not an accident, because the there is no there are no correlations for the coherent states in these angular variables. So if they are angularly separated, these functions which define the coherent states, then the states are product states, and you get full additivity of the relative entropies. And therefore, it is actually a very natural thing to get a area proportionality. You can even do this more suggestively by saying, okay, for the you take as functions defining the coherent state a function on the line of the u variable times a characteristic function with respect to the sphere, so the spherical degrees of freedom here of our cross-section. And then you see you indeed get as relative entropy the relative entropy of the excitation of this chiral conformal part times the area of the subset where this function chi here, characteristic function, is supported, viewed as a subset of the cross-section where the area scales with this r star squared. So this brings me to my summary. So a quantized scalar field on a spherically symmetric spacetime with an outer trapping horizon has scaling limits at any horizon cross-section independent of the choice of the chosen Hadamard state. So the scaling limit is the same for any Hadamard state, which induces a universal scaling limit theory at any chosen cross-section. The restriction of the scaling limit vacuum to the right hand side algebra, which naturally arises in this case, is a KMS state at inverse temperature, which relates in this way to the surface gravity of the horizon cross-section with respect to the Kodama flow induced in the scaling limit, which is the local analog of the Hawking temperature. I have skipped that this can be interpreted as a tunneling probability. The relative entropy of coherent states of any such scaling limit theory is proportional to the cross-section area. So that is, if you like, an adiabatic form of the entropy area proportionality in the scaling limit. And it very well fits with Wittgenstein's information theoretic interpretation of black hole entropy. And you can see this paper by Jolly, Longo, and Ruzzi as actually a quantized version of this Wittgenstein idea. At least I would do, and this then has this natural connection of this result I've presented to Wittgenstein's idea. So yes, one can also obtain the thermodynamical formula of the relative entropy to the energy of a coherent state times the inverse temperature. That's the thermodynamic relation. And one can also change some of the conventions entering in the scaling limit definition such that you actually get the proportionality in a natural way with this factor 1/4. I mean, for instance, we have included a factor 4 here in the scaling limit, which you may spot comes from these two factors 2 here. They have been inserted to give the scaling limit 2-point function this well, fairly canonical form on the horizon. It has always been given in that form because that's the scaling limit form of a, yeah. Okay, so there are reasons by convention for choosing that. But if you drop that, if you drop the factor 2 here in these slots, then you come up with this iconic cross-sectional area over 4 proportionality. Somehow my co-authors were not happy with doing it that way and wanted to emphasize that this depends on some conventions that one has to fix, but you can do that. And then, if you like, you get this iconic formula. Entropy is proportional to black hole area divided by 4. Okay, I think this was all I had to say. I hope I have not gone too much over time. But yeah, okay, that's it.
Okay, thank you, Rainer, for the nice talk. Questions?
May I ask a quick question, Rainer? Hi.
Yes, please. Yeah.
About the notion of a local temperature. There was a paper, old paper by Detlef Buchholz and Bros, I think, on the subject. Does it fit with you, with your work?
I think you are referring to the paper where they consider de Sitter spacetime, right?
No, the paper with the local KMS state, local.
Yeah, this was not with Jacques Bros, but yes, that would fit. Yeah, that would fit, I guess. Yes.
Yeah. Okay, thank you.
Other questions? Just a moment. Okay, Wojciech.
Yes, hello. So I have a general question about relative entropy. Is it possible to see in any way if the JNS representations of the two states which are arguments of the relative entropy give rise to disjoint representations or not?
What do you mean by joint representations?
Well, disjoint, not unitarily equivalent. Can I say something about if the states are from the same volume, for example, when I know the formula for the relative entropy? Or if there is
I'm afraid
BHR...
I cannot tell you, but my understanding is, and I think that is in keeping with what Daniela has said in the previous talk, that the Araki relative entropy is defined and gives a finite number for the case that these are states on the same von Neumann algebra, normal states, normal and faithful standard states. So I'm not aware, but I'm not an expert of a similar definition for more general situations. There may be, but I'm afraid I'm not expert enough to answer.
What I have in back of my head would be, of course, a singular coherent states like in the infrared problems. So your expectation is that it would just be infinity, the relative entropy. If
I would say, I would think that formally you would get infinity, yes.
Okay. I see, okay.
But you have to ask the experts. I mean, there are many in the audience. I'm afraid I'm not expert enough.
Because what is somehow suggests that by the literature from lattice models, Kitaev model, and so on, is that somehow the two states should satisfy a string-like DHR criterion if there is topological order, or if there is this proportionality of the entropy to the area. Somehow this is my impression when I read it. But now from your talk, I see that it is completely independent, but even for normal, for states from the same volume, I can get
yes, and even more special ones like coherent states. So I'm afraid I cannot now say much more about more general classes of states.
Okay, thank you.
Okay. Other questions? Helling, Robert Helling.
Hi, Rainer.
Hi, Robert.
Maybe you can elaborate a little bit more on the physical meaning of the scaling limit.
Yeah,
that has the physical effect, right? I mean, if I take a stupid scaling limit, I end up just with Minkowski space, and
maybe that
whatever
is
I want there. And this is obviously not what you're doing, but you're doing something to your theory.
Yes, of course. I'm looking, so to say, at an asymptotic part of the theory. That's right. So since people have been asking this previously, I came up with the following picture. I said, well, look at surface waves of water. Yeah. So that can be very complicated, and you can think of that here in comparison at the theory at finite scale. Yeah. Close to the horizon, if you like. And now you take a scaling limit. You look at your water at molecular scale. And what you see there is dominantly the Brownian motion. So these very complicated finite scale effects, they have gone. And you look at these thermal excitations, which are dominant at a small scale. And that actually compares to this situation that you have here, I think. Well, at least superficially, at this very catchy, heuristic way of looking at it.
Okay, thank you. I have to think about this.
Yes.
Okay, let us thank Rainer again. Now, we will be back in 20 minutes at 4:50 p.m. with the talk.